So let me tell you a little bit about linear systems, which is sort of the basic mathematical idea behind a lot of things related to machine learning and many other applications as well. So in a sense, a system from a mathematical point of view is just a fancy name for a function. So you are probably most familiar with functions from, say, calculus or maybe linear algebra, where you often have a concrete formula specifying how this function works. You study the function f of x equals x squared or something like that. And the basic way of studying this function is by manipulating the formula given for the function. Now, when we're doing linear systems theory, we are not really, most of the time, we're not really focused on the actual formula for this system. Instead, we're going to take a somewhat different viewpoint. So let me just give you some terminology here. So a linear system, I'm going to explain the linear part in a little bit, is a machine or a function mapping something we call input signals to output signals. And we're mostly going to study these as a black box model. And that means exactly that we don't really know exactly what's going on in this machine, how the function maps the input signal to the output signal. We might know a formula for how to do it, but in most cases we do not. And the signals we are looking at, they can be more or less anything, but most of the time they are functions themselves. So the input signal is maybe a function of one real variable. It can be a function of several variables, but in most of the examples we're going to look at, there will be a single variable function as an input, and it will be a single variable function as an output. A system that is set up like that, taking functions to functions, it's often called continuous time systems. Another kind of system is when we input a sequence. Well, if you want to, you can of course think of a sequence as a special kind of function as well, but sequence is then a sequence of numbers. It comes sort of in a discrete fashion, one at a time. And systems that take sequences of numbers to sequences of numbers are usually called discrete time systems. And let me tell you a little bit about the linear part of these systems. Actually, let's start with a couple of examples that may or may feel familiar before we're going into the linear part. So here's one example of a system in continuous time. This should be familiar to all of you. It's the system that differentiates the input. So you take a function, put it into our system, and out comes the derivative of the function. Now here we have a formula for the operation. Well, formula. At least we have a description of exactly how to compute the output signal given any input signal. We just differentiate. And here you might say, well, it's a problem. What happens if the function is not differentiable? Well, then it's not allowed to use as an input signal to this system. In most situations, we're not going to be too picky about specifying the domain of definition or the codomain or the value set for a system. To do this in a mathematically completely rigorous way, we need to write down the domains of definitions as well. But for the applications we have in mind, we won't be too concerned about that. So in this particular example, for example, if we plug in the input signal f of t equals sine t, we get cosine t as the output. If we plug in t squared, we get 2t, and so on. Here is our second example, an image filter. This is applying something called a Gaussian blur. I'm not going to tell you exactly what it is if you don't know it already. But here we have an example of a system that accepts an image as the input signal and outputs another image as the output signal. And as you can see here, this particular system blurs the image so that it becomes less sharp. And in this example, you could think of the input signal as a discrete two-dimensional object. So here we're dealing with discrete two-dimensional time, which is a little bit strange, but from a mathematical point of view, it's okay. So in fact, many of the systems you're going to look at when you're doing, for example, neural networks or other kinds of machine learning techniques, the input signal will be a finite dimensional discrete object, or an object that where time acts as a finite dimensional discrete space. So, for example, images, which are usually two-dimensional. This is a grayscale image, and here you can think of this image as for each pixel you output a value which is the blackness of that pixel. Of course, if this was a color image, then the signal itself would probably be a mapping from a discrete two-dimensional grid to maybe a four-dimensional or at least a three-dimensional output signal, separating the color of the pixel into a red, green, and a blue channel, for example. So what makes a system linear? Well, let me just remind you of a couple of things that you've probably seen earlier, for example, in a course in linear algebra. The basic concept here is linear combinations or superpositions, if you prefer. So if you have two signals, let's call them f and g, and two numbers, alpha, beta, and these numbers, depending on the application, these could be real or sometimes complex numbers, then we can form a linear combination of the input signal f and g by taking alpha times f plus beta times g, and we get a new signal. This is a superposition of, or a weighted superposition of f and g, or if you prefer, a linear combination of f and g. Now, what makes the system linear? Well, the property that makes a system linear, that it maps linear combinations to linear combinations, or more precisely, that if you have two signals and you form a linear combination of those, alpha f plus beta g, and send it through the system, you will get the same thing as if you first send the individual signals f and g through the system and then form the linear combination on the output side. And for example, if it's a simplest case where one of these constants is 0, let's say beta equals, that if you multiply the input signal by a fixed number like 2, say 2, then the output signal gets multiplied by the same fixed number. So, anyway. And for this to make sense, of course, you have to be able to add or form these linear combinations, both on the input side and the output side. So that means actually that the input to a linear system and the output to a linear system must be some kind of vectors. To be mathematically precise, there should be elements in some vector space. And in most situations, that won't be a problem, because we're going to just plug in any old function, or maybe continuous functions, or maybe differentiable functions, and we know that linear combinations of such things are, again, objects of the same kind. But in some applications, it might take a little bit more work to find the correct vector space where these input and output signals should belong. Anyway, linear systems preserve linear combinations. That's the main thing. So let's return to our first example, differentiation. So if we take the signal, or the system that maps an input signal f to its derivative f prime, then let's check that this is in fact a linear system. Well, we need to compute what happens if we send in a linear combination of two functions. So we need to compute how the system S acts on the input signal alpha times f plus beta times g. And we know that S just differentiates its input, so S will output the derivative of that linear combination. So the derivative of alpha f plus beta g, and using standard rules of differentiation, we know that this is just alpha f prime plus beta g prime. And here you see that here, of course, it's important that alpha and beta are constants. If alpha and beta also depend on t, you need to use the product rule, and you will get something more complicated. But for alpha and beta constants, this is just alpha f prime plus beta g prime. And of course, this in turn is alpha times the system response for the function f plus beta times the system response for the function g. So the linear combination alpha f plus beta g gets mapped to the linear combination alpha times s of f plus beta times s of g. And this is just saying that differentiation is a linear operator or a linear system. Let's take a couple of more examples. This is the system SF mapping the function f to the function t times f of t. Now here, notation quickly becomes a little bit tricky, or at least a little bit complicated, because input signal is actually a function. We want to plug in a function into the system S, and then we need to evaluate that at a certain point of time. So the notation here differs a little bit from book to book, but I think this is probably the best notation. None of the possible notations are perfect, but this is the least bad, I think. So this S of f of t should read as that you take the function f, plug it into the system S, and you evaluate at some point t. And the result should be t times the original function evaluated at t. So this this system just maps a function to a function times t. So if you plug in t square, you will get t to the third power as the output, and if you plug in sine t, you get t times sine t as the output. Now, is this a linear mapping or a linear system? Well, just let's check. We want to compute what happens with a linear combination. Combination alpha times f plus beta times g, plug it into the system S and evaluate at a certain point in time, you get t times the corresponding linear combination alpha f plus beta g evaluated at the point t. And if you untangle that mess of notation, you will see that this is just a way of writing alpha times tft plus beta times tgt with lots of more parentheses. And that in turn is the same as alpha times the system's response to the function f plus beta times the system response to the function g. And again, we see here an example of a linear system. Multiplication by function t is linear. And of course, there's nothing special about the function t. You can just do the same example by taking a system mapping f to a fixed function times f. This will also be a linear system with exactly the same argument. So let's finish off with an example that is not linear. So if we take the system S defined by saying that the input signal f is mapped to f times the derivative of f, then this is not a linear mapping or a linear system. How do we see that? Well, for example, if you plug in 2 times f, you will get 2 times f times derivative of 2 times f, and this is 2f times 2f prime, or 4f prime. But 4 times f of t, f prime of t, is not the same as 2 times the system response of f itself, because, well, 4 is not equal to 2. So here's an example of nonlinearity. And this is a sort of a typical example. If you multiply things that depend on the input signal, for example, as in this case, f times f prime, then you will not get linearity. The same thing is, for example, if you do some other operation on the nonlinear operation on the input signal, you take the input signal squared, or you take e to the input signal, something like that. Those systems will also not be linear. And the point here, of course, many systems that occur in applications or in nature are linear, at least to a first approximation. And it will turn out that linear systems are a lot easier to study than nonlinear systems, and we can say a lot more about linear systems and the behavior of linear systems, and that's one of the main reasons for studying them. Let's finish this off and continue in a second video.